Today we're going to look at a really nice differential equation, and this would be one that would be a bit trickier than in most introductory differential equations classes, but that being said, I think there are some nice tricks that we'll use to solve this. Okay, so we've got y prime equals y squared over x squared plus y squared minus xy. So we're going to take some motivation from the structure here, the fact that we see this y over x quantity squared, and introduce a new variable z. So let's set z equal to y over x. But observe that that's the same thing as saying that y is equal to x times z. And from that, we can use the product rule to see that y prime is equal to z plus x times z prime. Again, that's just by the product rule. So now what I want to do is take this substitution. Notice we've got a way to substitute for y and y prime and see what happens to our differential equation. So this left-hand side becomes z plus x times z prime. And then the right-hand side becomes z squared plus xz, both squared, so x squared, z squared. And then minus, let's see, x times y is going to be x squared z. So this is what we've got at the moment. But now let's move some things around. We'll have xz prime is equal to z squared plus x squared z squared minus x squared z, and then minus z. And observe that we can factor this if we look at it just right. So observe that we can pull a z out, and then after that, we've got something like this, z minus 1 times x squared plus 1. Now, you can multiply that out and see that that is exactly what we get there. Okay, so next up, we see that we have a separable differential equation at this point. We did not up here, but after substitution, we do. So we can move all the z's to one side and all the x's to the other side. That leaves me with what? So we've got z prime over z times z minus 1 is equal to, well, that's going to be x plus 1 over x. And now we can take the antiderivative of both sides with respect to x, keeping in mind that this left-hand side will essentially be the antiderivative with respect to z because of a change of variables. And what will we have? So we'll have the antiderivative dz over z times z minus 1 is equal to the antiderivative of x plus 1 over x. So now over here on this left-hand side, the standard thing to do would be to use a partial fraction decomposition. But I like another trick sometimes, and that is we're going to multiply the numerator as well as the denominator by z squared, or 1 over z squared. So there, in other words, I'm dividing the numerator and the denominator by z squared. So that's going to give me what? So I'll have dz over z squared in the numerator. And in the denominator, I have 1 times 1 minus 1 over z. So essentially what I do is I take this z squared that's in the denominator of the denominator, I cancel out this z, and then I cancel one term at a time from the z minus 1. And then let's see, over here, we can just take the antiderivative. We have 1/2 x squared plus the natural log of x plus a constant. And now what can we do here? Well, at this point, we can do another substitution. So let's set u equal to 1 minus 1 over z. But observe that means that du is equal to dz over z squared. And well, that's the nice trick that we did right here that allowed us to escape our partial fraction decomposition. So now this becomes du over u, which integrates out to the natural log of u, equals the natural log of 1 minus 1 over z. But now, using the fact that z is y over x, and then moving some things around a little bit, we'll see that this is the natural log of y minus x over y. Okay, so, but now we've got this term, this natural log of y minus x over y equals this whole term over here, this half x squared minus natural log of x. So what I'll do at this stage is I'll subtract this natural log of x to the left-hand side of the equation, and then use logarithm rules to bring this x inside the logarithm, and it'll be in the denominator. So that gives me the natural log of y minus x over xy equals, let's see, half x squared plus our constant. But now, of course, we can exponentiate both sides and end up with something like y minus x over xy equals a new constant, which is really the exponential of the old constant, times e to the x squared over 2. And you can go ahead and finish this off by solving for y, but perhaps I'll leave that as a homework exercise. And that's a good place to stop.